Section 6.1a is about solving inequalities by addition. We've already learned to solve equations by using addition properties, and now we're just going to add inequality symbols to the mix. This key concept here basically just says that if you have an inequality like this one, 2 is less than 7, and you add 6 to both sides, you end up with an inequality that's true. It's kind of like the scales idea back when we did something like this. 7 minus 2 equals 5. And we know that that's equal. Well, if we add 3 to both sides of the equation, we keep the scales balanced. And you can do something on one side of an equation as long as you do the same thing on the other. The addition property of inequality says the same thing, except now you're using an inequality symbol. Like 5 is less than 2, that's a true statement. So if I add 3 to both sides, it's still going to be a true statement, just like this one says up here. So here we have a couple of examples for inequalities, and we have to solve for the t, which means we're going to isolate this unknown. Well, the 45 is connected with subtraction, so to get rid of that, we're going to add 45 to both sides, just like we would do if it was an equal sign. So these cancel off, leaving a t is less than or equal to, this is going to be a 58. And there's my solution. Second one, 7 is less than x minus 4. The 4 is connected with subtraction, so we'll add it. So 7 plus 4 is 11, and 11 is less than x. Now there is something to note here in this one. I would suggest that you always put the letter on the left side when you finally write it. And the reason is because we're asked to graph it here. Now, if 11 is less than x, that means 11 is smaller than x, and I put the x over here and the 11 on the right, what do I have to do? Well, the answer is I have to change the sign. Because if 11 is smaller than x, that must mean that x is bigger than 11. So be careful that when you move the variable from the right to the left side in the very last step, you got to switch that symbol. Now it's easier for me to graph this. So I'm going to graph x greater than 11 on a number line. Here's 0. I'm going to say this is 11. I'm going to put an open circle there, and I'm going to shade to the right. And so that's what the graph looks like. We're going to go a little bit more in depth in graphing here in a little bit. I'd like to talk about one quick definition, set builder notation. This is a more concise way of writing a solution set, and I want to show you what it looks like. If we go back and use the example t is less than or equal to 58, set builder notation looks like this. It's almost identical to the answer that we had before, but what it does is it takes a letter on the left side and it says that letter is going to be my domain letter, and then it uses a bar to separate that from the solution and puts it in a squiggly bracket to show you that it's a solution set. That's all that set builder notation is. If I write the other one, x greater than 11 like this, here's what it will look like. Set builder notation is one of these things where I'm introducing it to you now. We probably will not use it for the rest of the year, but when you get more advanced level mathematics, you'll see it pop up again. So I want to introduce it to you. Here's some more examples of solving inequalities using addition. Subtracting 12 here, so I'm going to add 12 to both sides. So we end up with x is greater than, that's a 77. I'll write my answer in set builder notation. This one over here, subtracting a 9, so we're going to add 9 to both sides. 21 is greater than or equal to y. Remember I said it's better to write your answer with the y on the left, but that means I got to flip the sign. Set builder notation. I promised you a little bit about graphing, and here's where I want to compare the graphs of these two solution sets. This one here we've done in the past, and so I want to graph it on a number line. So I'll do that by starting with the number 2. And then going to 1, 0, -1, -2. Now, because these are all separated by commas, that means each individual number should have a blue dot on it. And because it has the 3 dots on the left side, the ellipsis, that means the pattern is going to continue forever. So if you remember, we referenced that by making a dark arrow. So that's how you would graph the top one. Now, here's how you'd graph the bottom one. There's their 2, and we want to be less than 2, less than or equal to 2. And I want to talk about the differences here. In the top one, if you notice, each one of these numbers is an integer. There are no fractions, there are no decimals. They specifically say 2, 1, 0, -1, and so on. So none of the numbers that are between any of these are included in my graph. So that's why I have to use dots. But down here it just says x is less than or equal to 2, which means I can include any number like 1 or 0.6 or negative 1.3 or anything that's in between any of the integers. The last thing I want to talk about is this dotted line, or excuse me, this filled in circle. Because it's less than or equal to, that's why I filled the circle in. The equal to part means that the circle is going to be filled in. If it just said less than, then I would have made this an open circle. So you see the contrast in the two ways of graphing. This is the one that we're going to use here in this chapter because we're dealing with inequalities. Here's an example where we put everything together, solve it and graph it. So we'll add the 9 using the addition property, and we'll rewrite it. Set builder notation, and then we'll also graph it. 21, it's less than or equal to 21, so my dot has to be filled in, and I shade everything to the left. So that's my solution, and that's the graph.